Hello, I'm Michael O'Connell, and in today's video we're going to solve a material and energy balance problem for a continuously stirred tank reactor. So what I have on the screen here is the problem that we are going to try to solve. We're going to start on the whiteboard today, and the problem actually tells us what we need to do, and specifically we need to make two differential equations. One is going to have to do with how the concentration of A is changing over time, and the other is how the temperature of material that's in our reactor, how that's going to change with time as well, and we'll use a differential equation to express that. And then the manipulated variable in this case is going to be the temperature of material that is our coolant. So we have a jacket around our reactor, and that is basically to keep it from overheating / exploding, because if you can see here, this negative delta HR, that is the heat of reaction, the enthalpy, and you can see that it's negative. And what that means is we have an exothermic reaction that's going to release a lot of heat, so that's what the cooling jacket is for. And that is a variable that we're going to manipulate, and all of that extra stuff where we look at what our expressions actually accomplish will be done in Python, of course. So take a second to look at these parameters and the values that are given for them, because that's what I'm going to use here. And I am going to start writing some equations on the whiteboard, and then we'll talk about how we can get some differential equations that will be useful for us in Python to solve this problem. The first thing I want to talk about here is the Arrhenius equation. And if you looked at the parameters that were given to us, and hopefully if you weren't able to, you can go back and pause the video and take a look at all the numbers that were given to us. The frequency factor was given as K naught. So typically the Arrhenius equation is written something like this with the letter A. Negative E sub A R T. Right? I'm sure you've seen that in chemistry classes, but this time this A, this frequency factor, was given to us as K naught. So why is that important? Well, the big thing to understand here is that we have the activation energy divided by the ideal gas constant R, and that's basically a scaling factor for how much the temperature is going to affect the frequency of your collisions. And obviously, the whole Arrhenius equation is used to calculate this K, which is our rate constant, which will be important for us because we know we have a first order reaction of A to B. Okay, so we can actually write that equation as well. So we would have some rate R equal to our rate constant, and it's first order, so this is just going to be times the concentration of A. Okay. Excellent. So back to the Arrhenius equation. The thing I want to say about that is that we need to realize that yes, this quotient of the activation energy and the ideal gas constant R is a scaling factor as it's divided by temperature to gauge how much the temperature is going to affect the frequency of collisions that occurs, and thus your rate constant. So if you have a higher frequency of collisions, you're going to have a higher rate constant, and thus your reaction rate is going to be increased, which makes a lot of sense. We know that this whole term with Euler's number, right, is multiplied by our frequency. And I think that these units, they were given in like inverse minutes, inverse seconds. So it's some frequency of collisions between particles that's occurring. So this is going to be between 0 and 1. Well, if our temperature is really, really, really high, this is going to go to 0. E to the 0 is 1. And that will mean that our reaction rate constant is equal to the frequency of collisions that is occurring. What that means for us is that at super duper duper high temperatures, every single collision is going to cause a reaction, because they're going to be happening at super duper high energies, and they're certainly going to overcome that activation energy threshold in order to be changed into product B in this case. Now, why does that make sense? Well, what is temperature. What is that actually telling us? Well, what temperature tells us, it tells us something about the motion of particles, specifically their kinetic energy. How fast are they going? If the kinetic energy is higher, then the temperature is higher. And we all remember, hopefully from physics, that the kinetic energy is 1/2 the mass times the velocity squared. So that also tells us that our particles here, if our kinetic energy is high at high temperatures, that velocity is super, super high. And in fact, we know it has to be because we know our particles aren't very big. So when they're moving that fast, when they collide, I mean, they are certainly going to have enough energy to overcome the activation energy and react. So that's just kind of an important thing to note. And as I said before about the E over R being a scaling factor for temperature, all that means is that if you have a super, super high activation energy, then the frequency of collisions, or at least your reaction rate constant, it's going to be very, very sensitive to temperature changes. But if it's super duper low and you don't need much energy to have your reactants react into your products, then the temperature changes aren't going to have as much of an effect. So I just wanted to make some remarks about that. Hopefully that was edifying. But for us, there was something very important we were given, and that was a parameter E over R, and it was given as 8750 Kelvin. So we can actually rewrite the Arrhenius equation as K, and that is the same K as this, but that will equal K naught E. And then 8750, now remember, in the Arrhenius equation, the activation energy is negative. So for us, it's actually going to be negative 8750. And yes, the R was the ideal gas constant, so we'll just divide that by temperature. Perfect, so that's our equation there. Okay, the other thing I need to comment on, so we have these two equations. There's one more that I would like to have before we dive into doing our differential equations, and that is the heat transfer. So obviously the whole point of this coolant that's flowing in is that heat always flows from hot to cold, right? We should all know that from thermodynamics. So it's going to take in the heat from here, right? Into the coolant. That's the whole point. Okay, now we were given something that suggests that, and that was UA. And I believe it was in joules per Kelvin minutes. Okay, which is good, right? We know that we're going to be dealing with rates. Specifically, we're going to need an equation for how the concentration of A changes with time. And then the problem also said that we're going to need one for the temperature of our reactor, how that's going to change with time. So we know that for all intents and purposes, the joules per minute, that's good. We want the rate of energy change, or in this case, it's going to be heat transfer. But this Kelvin temperature, that means the rate at which energy is exchanged between the coolant, or actually, sorry, it'd be between the material in our reactor and our coolant that we're putting in there. That is going to be based on the temperature difference between the two. So if there's a higher temperature difference, there's going to be more heat that's going to be transferred into our coolant. So this expression is going to be very easy to write, because what it's going to mean for us is that our rate of heat transfer of sorts, which I don't really know what exactly we should denote that as, maybe Q, like uppercase Q, but that's going to be based on UA times the temperature of our reactor minus the temperature of our coolant, okay? So also just keep in mind that UA, there is another equation for the rate of heat transfer. That is obviously going to depend on the amount of surface area that's exposed to the coolant and the distance between the two and all of that. But fortunately, they just give that to us as a constant UA, and we just have to multiply it by the difference in temperatures for the rate of heat transfer. So now I think we're ready to start writing our differential equations. let's derive a differential equation to describe how the concentration of A is changing. Specifically, we need to remember that we are going to do a material balance for this because A is given to us in a concentration, which means that we can balance the mass. And the way we're going to do that is with the age-old material balance equation, which is that some amount of accumulation is going to be equal to whatever goes into our system, and then we have to subtract whatever goes out of our system. Then there's one other thing that we actually have to subtract here. We want a differential equation for the concentration of A, because that's what our problem is telling us to do. But A is reacting to form B, which means once some A comes into this tank, some of it is going to be reacted and thus consumed. So that also needs to be taken into account, and we subtract that from our mass balance here. So let's use this concept to make a differential equation for the concentration of A. And as I said before, and I keep saying it because I just want to emphasize it so much, we want mass, okay? So we're given A inside our reactor as the concentration, which means that it's going to be in some units of moles per liter, right? And we can express this as a differential, right? It's going to be changing with time. But there is a problem here, right? Because although we have moles per liter, and then this time it'd be 1 times 1/minute, right, for our small increment of time there, we have this volume here, and I said we want mass. In this case, we're going to use moles because our concentration was given in moles per liter in the problem. Fortunately, the problem did also give us a volume for the tank, and that's exactly what we're going to multiply this by. And it was also given in liters, so notice that this all cancels, and we get a mass in moles that's changing per minute, per time. And that's exactly what we want, which means that this differential here is going to be multiplied by V. Okay, so that's our left-hand side. That's the rate of accumulation for A. Okay, excellent. Now, what do we need on the right-hand side? Well, what's going into our system? Well, we were given a flow rate going in, and then we weren't really given anything going out. So we can assume that the rate of material that's going in and the rate of material that's going out is the same, which is very, very good. But once again, that's going to be in some volumetric flow rate, and we don't want that. We want it in some mass that's moving per time through our system. But again, we can do that by multiplying by our concentration, right? So if we have a volumetric flow rate, right, that's like liters per second or something, we multiply that by moles per liter, we get moles per second, which is the same as our units over there. So I know I'm like harping this point a lot, but I just really, really want to convince you that this works. So we can factor out Q because it's going to be multiplied by both things. But here is something that will be key for us to understand. Okay, so this is going to be multiplied by CA that's going into our system, and then CA that's going out of our system. Whoops, it's supposed to be a subscript. We don't want a T that big. Okay, does that make sense? Because again, the volumetric flow going in here is, oh wait, that's the coolant. We don't want that going in here, going into our tank. This is Q, and this is Q. Okay, so that's why they're both multiplied. It's the difference because it's in minus out. An important comment about the concentration of A going out. We have our agitator in here, right, spinning around. And what that means for us is that when we have a continuously stirred tank reactor, or anything that is, quote, well stirred, you'll see in a lot of these problems, what that means is that the concentration of A that's in our reactor is going to be the same concentration that's coming out because it's all stirred around. It's not clumped up anywhere. That agitator is spinning around and everything is all mixed together, and then it's going out. So it's not just going to randomly change. like that once we have that given to us in the problem that it's continuously stirred. Okay, the last part of our mass balance here is the consumption. So we have some A that's reacting, it's becoming B, and that's given by our reaction rate R, which is set equal to the rate constant multiplied by our concentration of A, not raised to any powers or multiplied by anything, because our coefficients were given as just 1, and the reaction is a first order reaction. Okay, now if you remember from maybe a general chemistry class, as I said before, what units is R usually given in? From what I remember when I was taking exams, usually it's something like big M over S, and big M is molarity, which is moles per liter. Okay, so we have moles liter per second. Okay, that's good. So we can use that because we have our moles per second. So we can subtract K. A there. Actually, I should describe that as Ca. Sorry about that. But there is something that I have to emphasize here as well. Once again, back to our units. We want everything. This is the rate of change, in moles per second, because we're talking about the differential equation for the concentration of A. But we have a volume here once again. Oh, cannot stress that enough. What does that mean? Well, we need our volume of our tank again. We need to multiply this. All the units have to match. That's why I've been emphasizing this so much. And because we just want our differential term there with the concentration of A, we can divide all of this by volume. So I'm going to just rewrite that here. So, okay, we have the rate of change and the concentration of A with respect to time equal to the volumetric flow rate. Sorry, this is divided by volume. So the volumetric flow rate divided by volume multiplied by the concentration of A going in minus the concentration of A that's in the tank. Then we also need to subtract K times the concentration of A. We don't need to multiply by volume because we divided both sides of our equation by volume. Awesome. So that's our first differential equation for how the concentration of A is changing with respect to time. Now we're ready to do our energy balance. So I'm going to write this equation that you've probably seen. And this is one that I also actually used in physics as well when I was in high school. And that's that the change in enthalpy is equal to the mass times the specific heat multiplied by the change in temperature. Hi, I wanted to make a quick comment before the video continues. Obviously, this is coming after I have made the video, but there is something very, very important that I forgot to mention. The reason we're able to use the enthalpy or the heat of reaction, in this case for our energy balance, is because we're dealing with a liquid. So really what we're talking about is the internal energies, right? So we have the internal energy going in, internal energy going out, that sort of thing, right? Now, in this case, because we're dealing with a liquid, the specific volume of a liquid is going to be extremely small because liquids are rather dense, right? And you might recall, and you can look this up anywhere on the internet, Wikipedia, that the enthalpy is equal to the internal energy plus the pressure times the specific volume, right? And the other thing that I should say as well is that we can assume that the non-flow work coming from our spinning agitator is negligible because nothing is mentioned about it in the problem. But I just wanted to make that very clear. So in this case, the internal energy and the enthalpy are basically going to be the same thing, and that's why I use enthalpy in the video. So hopefully that clears up any confusion that there may have been without this insertion. So hopefully you enjoy the rest of the explanation. And this is going to be really useful for us, but let's apply that same principle of accumulation equals N minus out minus consumed to our energy balance. So what's going to be our enthalpy? That's going to be on our left-hand side, just like we have over here with our differential equation for the concentration of A changing with time. So let's think about this. Okay, first thing we need here, we need a mass. Big surprise, right? Well, we were given density, and because we were given one density, we can also assume that that's not going to change with time, although because we have a reaction and there's going to be different materials, it could change with time, but fortunately for us, it can be constant because we weren't given any other information. So that will be rho. Okay, that is visible. Perfect, and we know that the mass is density times volume, so we have that. Then we were given our specific heat, C, and that was in joules per gram Kelvin. And then we have our temperature change. Again, this is our differential equation. We're talking about that small incremental change, right? So we can write that as d Tr dt. Notice I'm using T sub R for the temperature that's in the reactor, and then T sub C for the temperature of our coolant. Okay? Because those are very different. You know, one of them is the variable that we're examining that's changing the temperature of the reactor. The other is our manipulated variable that we're going to change and see what happens when we code all of this in Python. Okay, perfect. So that's our left-hand side. Let's think about what's going in, right? So we have some, actually we don't need it, delta, that's kind of silly. We have some enthalpy going in, some going out, right? Another thing we have happening that we need to consider, actually, is we have some, I don't even know what to call this. I'll just call it H sub T for now. And what I mean by that is we have some heat that's being transferred from what's the material that's in our reactor to the coolant, right? So that's going to be leaving as well. And because we have an exothermic reaction, we do have a loss of heat. Obviously, there's going to be energy release for your exothermic reaction. So I'll just put exo for there. Okay, so that's what we have right there. And then now we're ready to substitute what we know and write an actual expression. Let's see what we can do here. Okay, so we have the enthalpy going in and the enthalpy going out. Let's use the same principle that we have over here with the mc times delta T. So what we have to remember is that we have equal volumetric flow rates. The flow going in is equal to the flow going out, and that, again, that's volumetric. So we can multiply that by density as well. I'm just going to erase those so that we have room. So that's going to be rho times, in this case, it'd be Q, right? Okay, so that's our mass per unit time. And then all we have to do is multiply that by our specific heat, which is in joules per gram Kelvin. Okay, so we have that there. And then, what do we need after that? Well, we need our kelvins, right? We need our temperature difference here. And we already have our time with Q, so we don't have to worry about that. Well, we have some temperature going in and subtract it from some temperature going out. Hopefully you know what comment I'm about to make. This temperature going out is the same as the temperature that's already in our reactor. It's the same comment I made about the concentration of A right here, okay? So, and again, the reason for that is because this is a continuously stirred tank reactor. It's well stirred, everything is well mixed. Okay, and then I'm also gonna make another comment about the fact that I'm using T sub R for the temperature that's in our reactor, and then T sub C for the temperature of our coolant. So I'm gonna write this as TRN minus TR, okay? Okay. Then we have the heat transfer, okay? Because our coolant is going to take heat, basically, or heat is going to flow to our jacket where there's a lower temperature. And that equation is already on an energy per time basis, right? If we remember this Q, this is joules per minute. Okay, that's already given to us. So we don't even have to change anything. I can literally just write TR minus TC. Okay, I think there might have been a small mistake I made here. So I think I subtracted the obviously. Okay, so the last thing we're going to do here, obviously, is we have a reaction that occurs. And I got a little mixed up. I am correct, obviously. It told us that we have an exothermic reaction. And heat is going to be released. But again, the whole point, like we have that heat, we have heat being transferred to the coolant. So that heat that's produced from the reaction, that actually is going to be added. So if you remember just a few minutes ago, I think I had minus XO. It probably should have been plus. But fortunately, we're good with that now. So what do we need to do for this? Well, our delta H was given to us. So we have the negative delta HR. And if you remember that this, and by the way, this would be on the right-hand side of the equation. I know I'm kind of running out of room there. Okay, so we're going to add this, as I said. So how much is there going to be of this? And we know that this was expressed per mole. Okay, well, this energy that's generated from our reaction is going to be proportional to the rate at which things are going on, right? The reaction rate, which is given to us by R. Okay, that's good. That's something we can work with. So now remember, this is on a per volume basis, so we're going to have to multiply that. So it'd be the volume times the reaction rate constant K times CA, right? And now we can kind of just check our units real quick before we jump into Python and start coding all of this. Now, obviously, the other thing we would have to do to simplify things, we want just the dt sub r over dt. Now, what is that? That is the rate, or this is the differential equation expressing how the temperature of material in our reactor is changing over time. So I just want to correct myself and make sure I'm saying that right. So let's check our units. So this was given in grams per liter, multiplied by liters in volume, right? And then this was joule per gram, Kelvin, multiplied by a change in Kelvin per second. Okay, units cancel, so Kelvin, gone, grams, gone, liters, gone, joules. Sorry, that wouldn't, I'm so used to being in seconds, 4 in minutes, okay. You get the point though, so we have that equal to joules per minute. And what that means is that these other 4 terms, they all need to be in the same units. And if they aren't, then we need to have either a fact, something to convert that, right? Okay, this is volume per minute, right? Or some rate. Actually, I think this is given in liters per second or something. I can't quite remember, I'm sorry. But we're not going to worry about the time unit. That's honestly the least of our concerns at this point. So really, we just want to make sure that these other units are right. So yeah, once again, grams per liter. So again, you'd have the grams per second. The grams would cancel with the specific heat. The kelvins would cancel with our temperature difference, right? So we'd have joules heat per time. Once again, we know this is heat per time. I already did that before. It's the same thing. Then we have this, right? This is the energy release because it's an exothermic reaction. It's usually joules per mole, and I think in this case it was given to us in joules per mole. And then, well, what is going to be the proportionality for that, right? How many moles are we going to have? Well, it's going to be based on the concentration of A that we have, right? So we have this rate, which is, again, that's molarity per second. Remember, molarity is moles per liter, so it's per volume, so we multiply by volume as well. Now, one last thing conceptually. Let's kind of think about this, right? So we notice here that this term is added, right? If we increase our concentration of A, we're going to increase the temperature. Notice another thing, that this term here is subtracted. So if the temperature of the material in our reactor is higher, right? This temperature difference is higher between the temperature of material in our reactor and our coolant temperature, then this is all subtracted, right? So we're going to decrease the temperature change over time, which makes sense. That's the whole point of the coolant. So I think what we have here is good, and I would say that we're ready to code this in Python. Now we're ready to code this in Python, so let's get started. I've already done what I need up here for my imports, and then I have all of the values that we were given in this table 2.3. The other important thing to note is that, as you can imagine, we're going to use scipy.integrate. We're going to use solve IVP because we are solving differential equations simultaneously. Now, why do I say that? Well, there is an important comment I want to make about these equations that I typed up in Word that I can reference as I write this code. And that is the fact that this K, which is our reaction rate constant from the Arrhenius equation, obviously it depends on the temperature, right? So that is important, but K also appears in our material balance equation, the equation we use for describing the change in the concentration of A with time, or with respect to time. So that is important, right? So the concentration of A changing over time, it does depend on the temperature in this case. So that is going to be important for us. Also notice here that TC here at the bottom, that again is our manipulative variable that we're going to change. So it started at 300, so I should just have it as 300 to start here. And then now we are ready to move on. So we need to define our function, and as we always do, we're going to be returning the right-hand side when we're using solve IVP. So yeah, so this is what we want. So we'll just use RHS, the independent variable, which is time, I'll just denote as t, and the dependent variable y. And then we have two dependent variables, right? So we can unpack that as the concentration of A and the temperature inside our reactor. So we can unpack that, perfect. And then what are we gonna return? Well, we're gonna return these equations, right? So this is the right-hand side that I'm gonna type up in here as well. So there are a number of mistakes that I would like to address here. So first of all, I accidentally put Tn over here. This should just be Tr, right? We have the temperature of the material going in minus the temperature of the material going out, which is the same as the temperature of the material that's already inside the reactor. So I am going to need to change that as well. So yeah, this is Trn, and then yeah, Tro or Tr0, that is not what we want. That's the initial temperature. So this is what we're going to want as Tr as well. The other thing I forgot is K. K is used in both of our returns, so we are going to need to express it. And we have K naught there. And then I already have numpy imported, so we can use that for the exponential term. And then this B is the E over R, which is going to be negative. So we divide that by the temperature there. Okay. I think everything should be good now. Okay, so what are we going to need to do next? Well, what we're going to need to do next is actually use solve IVP, right? So let's see what that's going to do for us, right? Well, what do we need to put in to solve IVP? Well, we need our right-hand side. We need a tuple for the time, if I remember right? Our time span. And I put in an end time, 10 minutes. Seems reasonable. Okay, what are we going to need next? Well, we're going to need our values. And we need to supply them in proper order, right? So this is going to be our concentration. So what is our initial concentration? That's Ca naught. And then what's our initial temperature? That is Tr naught. Okay, good. What's our method? Just like last time, let's use the Radeau method, the one I can't pronounce. I still am probably not pronouncing it right, and I'm sorry about that. Yeah, so dense output, and we want that as true, right? Because we're going to want this solution for us, so let's just make sure that works. Okay, V is not defined. That's not good. Oh, yep. Well, I guess that happens sometimes when you're negligent. So V, sorry, I'm just trying to make sure that it truly isn't there. What was V? Well, that's the volume of our tank, and that's going to be 100 liters. I'll put the unit on there as well, just to be precise. Let's just do runtime all. This all goes in order. Okay, we're good. So we have our solution, right? Okay, and then now we can start plotting. Okay, so let's define our solution. We'll call it sol. Or actually, let's just type it out, solution, right? So that's what it is. So we have our solution. Let's make some times that we're going to use for plotting purposes. This is where the linspace with numerical Python is really useful. So we'll go from 0 to our end time again. Let's do 500. Okay. And now what we're going to need is we're going to need our solution attribute, right? So let's see, where would we put that, right? So let's actually, here, we have two dependent variables, right? So we have our CA and our TR, right? Let's just unpack those first, okay? And that's going to be equal to our solution. And then what are we plugging in? We're going to plug in our independent variable, and that's going to be our all these right there, right? Okay, so we have that. Good, it works. Excellent. Now we are at the point where we can do the fig make subplots, okay? And I think I got this from Plotly, yep, as usual. And this time, now they're in different units, obviously. We have concentration and temperature, so we are going to want these to be different. So we're going to want 2 columns and then rows, just one row. So that way we have just side by side panels there. So that should be good for us. Fig.add. I always struggle with this part, like remembering how to write it, you know. So this first one, we'll just do the concentration, and there is all kinds of stuff it gives us. So, oh shoot, sorry, this is always going to be your T-plot. Your Y is going to be your concentration. Okay, your mode, well, we want to look at how this is changing, so we'll do lines. And we want this in row 1. Maybe it's rows. Can't tell. I'm being too lazy. I think it probably is rows. Whatever. It'll yell at me and scream if it's wrong. And then column 1 for this. And oh, the last thing I wanted to do, this is just kind of something I like. I just want to put a name because I don't like when it just uses trace or whatever it does. It's just kind of annoying. And let's just copy and paste this, okay? So that way we can do the same thing with the temperature in the reactor. And hopefully we get some good plots, and then I can talk about it, and then we'll be done. That is the goal here. Okay, let's just make sure everything looks good. Yep. Okay, good. Let's see what we get. Okay, we have a problem, and it gave me a lot of information here about what's wrong. Holy cow. I am so sorry. Maybe it's these? I don't know. Okay, that looks legitimate. Okay, that does look like what we want. Well, as we can see, it looks like we do reach some sort of steady state. So let me just increase the time span to like 100 and see what we get here. One more. Una más. Okay, perfect. Finally, let's look at our 2 cases. So I changed the time to 40, and then I dropped our coolant temperature to 290, which is our first case, and this is what we have here. Let's think about this to make sure that it makes sense. So we see that our temperature decreased, and once again, this is TR. So this is the temperature of the material that's in the reactor. This makes perfect sense because that's the whole point of the jacket and the coolant that we're putting in. Because this is an exothermic reaction, heat is going to be released, so the coolant is there to take in that heat after it is released with the reaction. However, here's the important thing to realize. So as our temperature drops, the reaction rate is going to change, right? So our reaction rate, here's our reaction rate constant, K, right? So as our temperature drops, we are going to make this smaller, right? This K naught. So we're going to have less, the collisions are going to be less frequent, right? Our reaction rate constant goes down. And thus, the rate at which A is going to be consumed and converted into B, because there's going to be less collisions with enough energy, there's going to be more A. There's going to be more A left in your reactor because the stuff that's in there, this compound A, it doesn't have enough energy because the temperature has dropped down. It doesn't have enough energy to overcome the activation energy and convert to B. And now, as you can see, okay, what did it give us for the okay, it said it was 1 going in. And so, like, yeah, I mean, it gets close to that. So there's some reacting, but it's very, very, very little. Okay, so I think that all makes sense. Let's look at our final case. So the other one we were going to do is we're going to raise this to 305. Now let's see what happens with this. Oh boy. Oh boy. This is not good. Look at that. I mean, our temperature goes nuts, right? So that's just a very, very small change, right, in the coolant temperature. We increase the coolant temperature, we decrease the amount of cooling. Again, this is an exothermic reaction, so we see a bunch of heat released. So, just as I was just explaining, what do you think is going to happen to A if this goes up super high? It's just what I said in the very beginning of this video. Let me pull this up again. This Arrhenius equation, it's pretty great. It's pretty useful. It makes a lot of sense, right? So our temperature spiked, which means the frequency of collisions is going to increase. Our reaction rate is going to increase, which means the rate at which A is being consumed this time is going to increase. So, as you can see here, we started at 0.5 for our concentration of A. It drops down precipitously, right? And then we have all that energy being released. And then again, we decrease the cooling, so the temperature goes up. Okay, now what happens here at the bottom? Well, eventually, the reason the temperature actually drops back down is just there's no more A to react. There's hardly any left. So to restart kind of that process again, that exothermic reaction that's going to occur, the temperature has to drop because, again, there's just no more A there's hardly any A left to react. So as the temperature goes back down, right, as that drops, we're going to see the concentration of A increase. Okay, so these are just like inversely related there, right? And then this process repeats again. So as this goes up, right, we have the temperature going down. Okay, then we have the temperature going up again, and then the concentration of A is going to decrease. The last thing I want to say before we wrap up this video is this simply highlights the importance of simulating processes, especially with these reactors. When we're doing exothermic reactions, lots of heat is released, explosions can happen, and people get hurt, and that is not what we want. So that is honestly the importance of this whole problem that we're doing today. But hopefully you enjoyed the process of solving that problem, how we used a material balance and an energy balance to do this. And obviously, it's always good to be using Solve IVP. It's just great coding practice because it's used so often to solve simultaneous differential equations. So hopefully all of that was very edifying, and hopefully a lot of this helps you understand the Arrhenius equation, and maybe a lot better than maybe you understood it when you took general chemistry. So thank you so much for watching.